Section 4.3, we're talking about greatest common divisor and least common multiple. Let's start by looking at the definition of each one of these words. The greatest common divisor, also known as the greatest common factor, is abbreviated with GCD or GCF, depending on if you want to say divisor or factor. These are the same thing, and what they are is basically looking at two numbers, like A and B, that are whole numbers, not zero. So let's look at maybe 24 and 30. We might ask, what is the GCD of 24 and 30? And basically what this is you'll make a list for each number's divisors and pick the biggest one out of the list. Let's make a list of our divisors. The divisors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. If you're curious on where I got these numbers, go back to section 4.2. Let's also make the list of divisors for 30. The divisors of 30 are 1, 2, 3, 5, 6, 10, 15, 30. If we're asking about the greatest common divisor, that means we're considering all possible divisors and then noting which ones they have in common. Notice that we have a few common divisors. We have 1, 2, 3, and 6. These numbers are both divisors. These numbers are all divisors of both numbers 24 and 30. But if we're looking for the greatest common divisor, then we should pick 6, because out of all possible divisors that they have in common, 6 was the greatest. Now let's take a look at the least common multiple, often abbreviated with LCM. The LCM is also looking at maybe two numbers. Let's use the same ones, 24 and 30. If we're looking for the LCM of 24 and 30, then I need to list out all the possible multiples of 24 and 30. We'll start off with 24 times 1, 24 times 2, 24 times 3, 24 times 4, 24 times 5, 24 times 6, and we don't really know exactly how far to go in this list of multiples, so we might have to come back and extend it. But for now, let's stick with just the first 6 multiples, and then let's take a look at the first 6 multiples of 30. So 30 times 1, times 2, times 3, just kidding. 30 times 3 is not 180. 30 times 3 would be 90. 30 times 4 would be 120. 30 times 5 would be 150. 30 times 6 would be 180. Looking at our list of multiples, we want to see if there are any in common. 24 is not common with 30. 48 is not common with 30. 72 is not. 96 is not. Oh, but 120 is. I see 120 appears in the multiples of 24. 120 also appears in the multiples of 30. This is the first multiple. If I had continued my list of multiples, I would find more of them. And they would get bigger and bigger and bigger. If you notice our multiples list, the numbers get larger as we continue. So the first multiple is going to be the smallest multiple. In other words, that's our LCM. Now, the two examples we just did, looking at the GCD and the LCM of 24 and 30, we did these in a very lengthy process where we just followed the definition of what each of these are, listing out either the divisors and picking the largest or the multiples and picking the least. But in this section, we're going to find more efficient ways to calculate a GCD and an LCM, especially when the numbers get very large. Before we do that, let's use the GCD in an application. So our GCD. Here we're talking about two bands, and they're going to march in a parade together. We have one band with 24 members, one band with 30 members. We want to combine them so that when they're lined up, they have the same number of columns. So I want to make sure that my 24-member band can be lined up in the same number of columns as my 30-member band. And then the question asks, what's the greatest number of columns which they can march? So let's list out our possibilities. In our 24-member band, we could have one column with all 24 members in the column. We could have two columns, and we could put 12 in each column. I notice I'm going to write the same things over and over here, so let's make a table. Let's make a table where the left side is the number of columns, and the right side is the number of members in each column. Okay, so we could have one column with 24 members in that one column, two columns with 12 members in each column. We could do three columns. If we did that, we'd have 8 members in each column. 4 columns, that would be 6 members in each column. 6 columns, that'd be 4 members in each column. We could do 12 columns, that would only be 2 members in each column. Or we could do 24 columns with exactly 1 member in each column. So those are all the possibilities for our 24-member band. Let's do the same thing for our 30-member. Our 30-member band could be arranged in one column with all 30 members in that column. Or we could do 2 columns with 15 members in each column. We could do 3 columns with 10 members in each column. We cannot make 4 columns evenly because we wouldn't have the same number of members in each column. So 4 is not an option for the 30-member band. We could do 5 columns with 6 members in each column. We could do 6 columns with 5 members in each column. We could do 10 columns with 3 members in each column. We could do 15 columns with 2 members in each column, or we could do 30 separate columns with 1 person in each column. Now that we have all of our possibilities listed out, let's go through and see which column numbers match up. So they both can be arranged in a column, just a single column. But remember that the question asks for the greatest number of columns, so maybe 1 is not the best answer here. 2 also works, and since 2 columns is more than 1, we know we're not going to use the 1 column option. 3 also works, eliminating 2 as our best answer so far. 4 is an option for the 24-member band, but not the 30-member band, so we will not pick 4 columns. 5 is an option for the 30-member band, but not the 24-member band, so we won't pick that option. They do both fit in 6 columns, so that's bigger than 3. We'll ignore the 3 answer for now. And if we look through the rest of our list, we'll notice that 6 is the last matching number, meaning 6 is the greatest number of columns which both bands can march. Let's look at a visualization of greatest common divisor. What you're looking at on the screen are called Cuisenaire rods or color rods. Each rod is a different length corresponding to one of our 10 digits. Actually, we don't have a 0 rod, so this is going to correspond to the whole numbers 1 through 9. Each one is a different length as well as a different color. We can use these rods to help decide what is the greatest common divisor between two numbers. So if we're looking at the common divisor for 8 and 6, we would pick the 8 rod, this dark blue rod, and the 6 rod, this gray rod. And we would look for all the possible divisors by comparing it to the other colored rods. So what we have in this picture is an 8 rod with a bunch of unit rods stacked up to it. And if we can stack unit rods so that they fit perfectly the same length as the 8 rod, then we would say that that unit rod divides the 8 rod. Same for 6, we stack up a bunch of units. We can see that those units stack up evenly, matching the length of the 6. So we know that 1 divides each of our numbers 8 and 6. Looking at our next rod, we have the 2 unit rod. So we stack up the 2, compare it with the 8. They do match up to be the same length. So 2 divides 8. And we can see visually that 2 also divides 6. Using the 3, the pink rods, we can see that 3 does not divide 8 because when we stack up the 3's, if we left this last rod off, then our stack would be too short for the 8. If we add this last rod on, it's too long for the 8. So no matter what we do here, we can't stack up pink rods so that it matches the length of the 8 rod. Looking at 3 with the 6, we can see that 3 does divide 6 because the rods line up evenly. 4 divides 8 because the yellow 4 rod matches up. 4 does not divide 6. The same problem we had with the 3 pinks and the blue 8, we have here with the 4 yellow and the gray 6. They don't match up, so we know that 6 does not have 4 as a divisor. We can see that 5 does not divide 8, the rods don't stack up, and 5 does not divide 6, the rods don't stack up. 6 does not divide 8, that gray rod does not match up perfectly with the blue. However, 6 does divide itself, those rods match up perfectly. 7 does not divide 8, 7 does not divide 6, Now here I've changed the order of the rods. 6 is on top this time, 7 is on bottom. I put the bigger rods on bottom in general. But we used multiple rods here because 6 is the thing that we're looking for divisors or factors of. So in some cases we just have to put a couple of our 6 rods to see that it works, but we'll see that that's more of a common multiple thing. But at any rate, it doesn't matter how many 6 rods and how many 7 rods we stack up, they never meet at the same point. 8 does divide 8, but 8 does not divide 6. We can look at all of our divisors, noticing that any stack of rods that goes to the exact same distance as the 8 rod, or any stack of rods that goes to the exact same distance as the 6 rod, those are our divisors. So for 8 we have 1, 2, 4. Those are the divisors of 8. For 6 we have 1, 2, 3, and 6. Those are the divisors of 6. And if we wanted to pick out the greatest common divisor, we're just going to look for the longest rod that fit into both visuals. That would be the rod 2. So the largest number that appears in both of these lists is 2. So our GCD is 2. Another way to find a common divisor is to use the intersection of sets method. So if we list out all of the divisors of 8, we can put those in one of our circles. And if we list out all of the divisors of 6, we could put those in one of the other circles. Notice that we do have a couple common divisors. 1 is a divisor that appears in both visuals. 2 is also a divisor that appears in both of our sets here. Remember that when we use the Venn diagrams, anything that appears in both needs to go into the intersection. And then we'll put the remaining divisors of 8, 4, and 8 inside of the red circle, but outside of the blue circle. And the remaining divisors of 6, 3, and 6, we'll put those in the blue circle, but outside of the red circle. This helps us separate all of the divisors so that we can see the ones that we do have in common a little more easily. And then from here, we'll just select the largest number in our intersection. This is the largest number in the intersection. Therefore, that would be our GCD. So the GCD of the numbers 8 and 6 is 2, just like it was before, but here's just another visual. Let's try this again, looking at the numbers 20 and 32. So I'll put the divisors of 20 in the red circle, divisors of 32 in the blue circle. Checking for anything in common, they both have 1 as a divisor, they both have 2 as a divisor, they both have 4 as a divisor. 20 also has the divisors 5, 10, and 20. 32 also has the divisors 8, 16, 32. Looking at our list of divisors in the intersection, I'll pick out the largest number. And identify that as our GCD. The greatest common divisor of 20 and 32 is 4. We can also use prime factorization to find our greatest common divisors. I have a few different examples here on the screen. We're going to try each one at a time. So working with problem A, We're looking for the greatest common divisor of 108 and 72. Now, you might be able to identify the greatest common divisor just by memory, and if that's you, great. But remember that when you're teaching this to someone for the first time, they might not have these facts memorized. So it might be more difficult for them to find the greatest common divisor if it's not something that they have memorized. So in that case, we can try the prime factorization method, which says to prime factor each number completely down to primes. So let's prime factor each number. Take a second, do that. Remembering our techniques from the previous lessons, we can find the prime factorization of 108 as well as the prime factorization of 72. Now to find the greatest common divisor using the prime factorization method, we're going to look at the common prime factors. So in 108, we have 2 factors of 2 and 3 factors of 3. In 72, we have 3 factors of 2 and 2 factors of 3. And we want to go through and look at whatever prime factors they have in common. So 108 has 2 2's, so does 72. Now notice that 72 has more 2's, but I can't circle or square in all 3 of them because 108 doesn't have that third 2. And same with the 3's. 108 has 3 factors of 3, but 72 does not. It only has 2 of them. So as far as what they have in common, they have 2 factors of 3 in common. So our GCD for 108 and 72, it's going to look like what I have in boxes. So 2 squared times 3 squared. And if we multiply that out, we get 36. And what's pretty neat is that we can rewrite 108 as 36 times 3, the factor that we left over. And 72, we can write that as 36 times 2, the factor that we had left over. So when we write it like this, we can see why sometimes it's called the GCF, because we're looking at greatest common factors. 36 is a factor of 108 because 36 times 3 is 108. 36 is a factor of 72 because 36 times 2 is 72. Let's take a look at our next example, the GCD of 0 and 13. If we prime factor 0, well, there is really no prime factorization for 0 because 0 is not prime or composite. Actually, you could call 0 composite. Ooh, that's tricky. Ooh, think back to the definition of prime and composite. Both of those definitions say the number has to be greater than 1. So 0 is not prime, it's not composite, it's this little limbo number. But as far as divisors of 0, what are the divisors of 0? It's actually all real numbers. Any number can divide 0. What about 13? Well, 13 is prime, so our divisors are 1 and 13, and that's it. So if we wanted to pick out the greatest common divisor between 0 and 13, looking at our list from 0, it's every number you could imagine. If you look at the list from 13, we only have 1 and 13. Now 1 is definitely in the list of all numbers I can imagine. 13 is definitely in the list of all numbers I can imagine. So the greater of the two choices we have would be 13. This will be true for the greatest common divisor of 0 and any number. So the greatest common divisor between 0 and 130, it would be 130. The greatest common divisor of 0 and 2 million, it would be 2 million. So whatever the other number is, because 0 has all the numbers as divisors. Moving on to our next example, we're looking at the greatest common divisor of the product, 23 times 72 times 11 times 13, and the other number, 2 times 73 times 13 times 17. Now, your first instinct might be to multiply these numbers together, but if we're using the prime factorization method, what we ought to do is start with this factorization, see if we can take it any further, meaning if there's any composite numbers in this list, we should break them down. And then from there we can finish with the prime factorization. So 23 times 72 times 11 times 13, is this prime factored? It's not. And the reason that I say it's not is because 72 is not prime. So really we could write this as 23 times 9 times 8 times 11 times 13. This is now prime factored. The next number we're looking at is 2 times 73 times 13 times 17. In this list of products, 2 is prime, 73 is prime, 13 is prime, 17 is prime. So this is prime factored. All we need to do is look for any numbers in common. They both have 13 and nothing else. So the greatest common divisor or greatest common factor would be 13. Now you could multiply these up and then refactor them, but that would be a lot of unnecessary work. So if you're asking about a common divisor and the numbers you're looking at start off factored, leave them factored and continue to factor them if possible. Moving on to our next example, we're looking at the greatest common divisor of the product 2 cubed times 7 squared times 11 times 13, and 2 times 7 cubed times 13 times 17, and 2 to the 7th power times 7. So we're looking at 3 numbers here, not just 2. Anytime you're looking at the greatest common divisor of 3 numbers, it's super important to remember that the divisor has to work on all 3 numbers. So looking at our products here, we have 2 times 2 times 2 times 7 times 7 times 11 times 13. That's our first number. Our second number is 2 times 7 times 7 times 7 times 13 times 17. And then our last number, we have 3, 4, 5, 6, 7 factors of 2, 1 factor of 7. Our greatest common divisor must divide all 3 of these numbers. So I see 1 factor of 2 that shows up in all 3 numbers, but notice that in our middle number here there are no more 2's, so the rest of these won't show up in our GCD. And then I see 1 factor of 7 that shows up in each number. But because our last number only has 1 7, the remaining factors of 7 in the other numbers don't show up in our GCD. 11 doesn't show up in any other number. 13 does show up in 2 of the numbers, but not the third, so 13 is out. And then 17 doesn't show up in any other number. So the only thing that showed up in all three numbers was a single factor of 2 and a single factor of 7. Multiply those together to find that our GCD is 14. 14 divides each one of these three numbers. One last example using this prime factorization method. We're looking at the GCD of 5 to the 4th power times 13 to the 10th, 3 to the 10th times 11 to the 20th. Now, each one of these numbers has multiple factors of the same prime numbers, meaning 5 to the 4th has 4 factors of 5 in it, 13 to the 10th has 10 factors of 13, but notice that 5 and 13 do not show up in our second number. 3 and 11 are the only factors in that second number, and they don't show up in our first number, which means they have no common factors. Except for 1. Remember that 1 divides every number, so in the list of common divisors, the only number that they will have in common is 1. Before we move on to that, we actually consider these two numbers to be relatively prime. They're not necessarily prime numbers because they have factors other than 1 in themselves, but they're considered relatively prime to each other. So relative to each other, we can call them prime because they don't share any common factors. Two numbers whose GCD is 1, or two numbers whose GCF is 1, are considered relatively prime.